Imagine a city, a bustling metropolis, thriving under a relentless, scorching sun. A city where the mercury routinely climbed to unbearable heights, yet its inhabitants enjoyed a degree of comfort we often associate only with the hum of modern air conditioning. This wasn't some futuristic utopia, but a reality thousands of years ago, long before the invention of electricity, refrigerants, or even a basic fan. How did they do it? How did ingenious minds, with only rudimentary tools and an intimate understanding of their environment, manage to engineer comfort in the most extreme climates? This profound question lies at the heart of a fascinating paradox. While our modern world grapples with escalating energy costs, strained power grids, and the undeniable impacts of climate change, we often overlook a rich tapestry of solutions woven by our ancestors. Ancient civilizations, from the arid plains of the Indus Valley to the sun-baked landscapes of Persia, mastered the art of passive cooling. They didn't fight nature with brute force and endless energy. They danced with it, harnessing its rhythms to create livable spaces. Yet, today, our architectural practices frequently ignore these sustainable blueprints, opting instead for energy-intensive mechanical systems. Consider the ancient city of Mohenjo-daro, a marvel of urban planning dating back to 2500 BCE. Nestled in what is now Pakistan, a region notorious for its searing summer heat, it boasted an intricate layout designed for optimal airflow and natural ventilation. Its buildings were thoughtfully oriented, streets strategically aligned, and even its sophisticated water management system played a role in mitigating heat. Then there are the iconic Persian wind catchers, or badgirs, towering structures that dot the skylines of ancient Persian cities. These elegant architectural elements weren't just decorative. They were highly efficient air conditioning units, naturally drawing cool air into homes and expelling hot air without consuming a single watt of power. These weren't isolated experiments, they were widespread, proven solutions. The irony is stark. We live in an era of unprecedented technological advancement, with supercomputers and smart homes, yet our approach to cooling often feels primitive in its reliance on brute force energy consumption. We build glass towers that trap heat, then spend astronomical amounts of electricity to cool them. We seal ourselves off from the natural world, creating artificial climates that are both expensive to maintain and environmentally taxing. This modern paradox begs a critical question. Why, with such a rich legacy of sustainable design, have we largely abandoned these time-tested methods? The relevance of these ancient solutions has never been more pressing. As global temperatures continue to rise and energy prices fluctuate wildly, the financial and environmental burden of mechanical cooling systems escalates. Our reliance on air conditioning alone accounts for a significant portion of global electricity consumption, contributing directly to carbon emissions and straining our infrastructure. Imagine if every new building, every urban development, drew inspiration from Mohenjo-daro or incorporated the principles of a badgir. The potential for reducing our energy footprint, lowering utility bills, and creating more resilient, comfortable communities is immense. It's not about reverting to the past, but about rediscovering wisdom that can inform a more sustainable future. The answers to some of our most pressing modern challenges might just be found in the sun-baked bricks and ingenious designs of civilizations long past. Before we continue, subscribe to the channel and tell us in the comments where you are watching from. The genius of these ancient solutions wasn't magic. It was a profound understanding of fundamental architectural principles, honed over centuries. At its core was the concept of thermal mass. Imagine colossal, thick walls crafted from adobe, stone, or brick. These weren't merely structural. They acted as sponges for heat. During the day, as the sun beat down, these massive walls slowly absorbed the intense solar radiation. But crucially, they absorbed it without immediately transferring that heat indoors. As night fell and the desert air cooled, these same walls would gradually release the stored heat, warming the interior just enough to stave off the chill, creating a more stable and comfortable indoor temperature range than the extreme external fluctuations. This slow absorption and release created a thermal flywheel, moderating internal temperatures without any active energy input. Alongside thermal mass, Ventilation was paramount. Ancient urban planners were masters of airflow. Take Mohenjo-Daro again. Its streets were often oriented to catch prevailing breezes, channeling them through the city. Houses were designed with multiple openings, not just for light, but to create cross-ventilation. Courtyards, a common feature across many ancient civilizations, were not just aesthetic spaces, they were vital cooling engines. In a typical courtyard house, the shaded central space would remain cooler than the surrounding sun-baked exterior. This temperature differential would draw air in, creating a gentle, natural convection current that circulated cool air through the adjacent rooms. Narrow streets, often perceived as quaint, served a crucial purpose, shading each other and reducing the overall heat gain in the urban fabric, creating cooler microclimates at ground level. Shading was another non-negotiable element. From the deep overhangs of traditional Japanese homes to the pergolas adorned with vines in Mediterranean villas, every architectural detail was considered. These elements blocked direct sunlight from hitting walls and windows during the hottest parts of the day, dramatically reducing heat absorption. Strategically planted vegetation, such as trees and shrubs, provided further shade, and through evapotranspiration, released moisture into the air, creating a localized cooling effect. It was a holistic approach, where every element of the built environment worked in concert to mitigate heat gain. Delving deeper into specific case studies reveals the ingenuity. Mohenjo-Daro's sophisticated urban planning extended beyond street orientation. Its advanced drainage system, with terracotta pipes carrying wastewater away, prevented stagnant, heat-absorbing pools. Some scholars even suggest the presence of rudimentary air shafts within buildings, designed to draw cooler air from shaded lower levels. The Persian wind catchers, or badgirs, are perhaps the most iconic example of ancient passive cooling. These elegant, chimney-like structures, often adorned with intricate patterns, captured prevailing winds. Internal baffles directed the air downwards into the building's interior, often passing it over subterranean water channels or cisterns, which further cooled and humidified the air through evaporation. Simultaneously, the warmer, lighter air inside the building would rise and be drawn out through other shafts of the badgir, creating a continuous, natural air conditioning system. It was a marvel of aerodynamic engineering, long before the principles were formally understood. In the Roman Empire, the atrium and peristyle courtyard served similar functions. The open-roofed atrium, often featuring a shallow pool, collected rainwater but also created a cool, humid microclimate that permeated the surrounding rooms. The larger peristyle garden courtyard, surrounded by colonnades, provided shade and greenery, acting as a central cooling lung for grander homes. Across the Atlantic, the Mesa Verde cliff dwellings, carved into the natural alcoves of canyon walls, are a testament to leveraging natural formations. These ancient Puebloan structures were strategically positioned to receive maximum sun exposure during the winter, providing passive heating, while the massive cliff overhangs provided deep shade in the summer, keeping the dwellings cool. They were inherently integrated with their environment, not imposed upon it. Material innovation, though often overlooked, was crucial. Adobe, a mixture of earth and straw, was readily available and possessed excellent thermal mass properties. Stone, with its high density, also served as a natural heat sink. Even water itself, beyond its use in badgirs and impluvia, was employed for evaporative cooling through fountains and shallow pools within courtyards, lowering ambient temperatures. Were these techniques truly lost? Perhaps not entirely. The principles remained, passed down through generations of builders. But the Industrial Revolution, with its promise of cheap energy and novel materials like steel and glass, gradually shifted architectural priorities. The ability to mechanically control indoor climates began to overshadow the nuanced, site-specific wisdom of the past. The intricate dance with nature was slowly replaced by a brute force approach, setting the stage for our current predicament. The Industrial Revolution, a period of unprecedented technological advancement, profoundly reshaped human civilization and, consequently, our built environment. The advent of mass-produced steel, large glass panes, and reinforced concrete offered architects and engineers new freedoms, allowing them to construct taller, wider, and more open structures than ever before. This era, fueled by the promise of abundant and increasingly affordable energy, began to divorce buildings from their natural surroundings. The need for thick, thermally massive walls diminished when mechanical heating could simply overcome the cold, and large windows, once considered a thermal liability, became symbols of modernity and transparency, despite their heat gain implications. The intricate dance with nature, the careful consideration of sun path and prevailing winds, seemed less critical when the flick of a switch could apparently solve any comfort problem. Then came the widespread adoption of mechanical cooling, air conditioning. Invented in the early 20th century, air conditioning started as a luxury, primarily for industrial processes and then for grand public spaces. But as technology advanced and electricity became more ubiquitous and cheaper, ADAS units rapidly permeated homes and offices, transforming our expectations of comfort. Suddenly, buildings no longer needed to be designed to mitigate heat. They could simply be sealed boxes, and the interior climate could be brute-forced into submission. This perceived solution allowed for architectural styles that were often thermally inefficient, prioritizing aesthetics and speed of construction over natural climate control. The glass-clad skyscrapers that dominate modern cityscapes, while visually striking, are often energy guzzlers, relying entirely on HVAC systems to maintain habitable temperatures. The economic drivers behind this shift are undeniable. In many development models, the upfront cost of construction often takes precedence over long-term operational efficiency. Building faster and cheaper, even if it means higher energy bills for decades, can be more attractive to developers. Furthermore, the industries that produce and install air conditioning units, insulation, and other mechanical systems have become powerful economic forces, creating a vested interest in maintaining the status quo. Regulations, too, have sometimes lagged behind, with building codes focusing more on safety and structural integrity than on holistic energy performance, although this is slowly changing. The consequences of this trajectory are now starkly evident. Our reliance on energy-intensive cooling contributes significantly to carbon emissions, exacerbating climate change, the very problem we often seek to escape indoors. Power grids groan under the strain of peak summer demand, leading to blackouts and increased energy costs for everyone. The urban heat island effect, where cities are significantly warmer than surrounding rural areas, is intensified by the heat expelled from countless air conditioning units. We've created a cycle of dependency, where our comfort is inextricably linked to a system that is unsustainable in the long run. However, there is a growing movement to reevaluate this ancient wisdom. Contemporary architects and urban planners are increasingly looking to the past, not as a nostalgic exercise, but as a source of practical, sustainable solutions. Projects worldwide are integrating passive cooling techniques into modern designs. Think of buildings with double-skin facades that create a thermal buffer, or public spaces designed with shaded courtyards and water features that evoke Roman peristyles. Green roofs and vertical gardens are not just aesthetic additions, they provide insulation and evaporative cooling. Sophisticated building management systems now leverage sensors to optimize natural ventilation and shading, blending ancient principles with cutting-edge technology. The path forward requires a fundamental shift in mindset. We must move beyond the notion that comfort is solely achieved through mechanical means and recognize the profound intelligence embedded in ancient architecture. It's a call to action for urban planners, policymakers, developers, and even individual homeowners to demand and implement more sustainable building practices. By blending the time-tested wisdom of Mohenjo-Daro, the ingenuity of Persian wind catchers, and the natural integration of Mesa Verde with modern materials and computational design, we can forge a greener, more resilient built environment. The future doesn't have to be hotter and more energy-dependent. It can be cooler, more comfortable, and more harmonious with the planet, by simply remembering how our ancestors built. The answers, often, are not new inventions, but rediscovered truths, waiting for us to